focus for this lesson is on biconditional statements. And we have already seen conditional statements, something of the form P implies Q. We also saw conditionals with the format if, hypothesis, then conclusion. Furthermore, when we examined conditionals, we saw how to write out the inverse, the converse, and the contrapositive. Our objective when working with biconditionals builds on that. We want to see how to write out a biconditional statement today. We want to see what the notation is, what symbols we use to represent them. And then we also want to evaluate the truth. So is it overall true or overall false? Recognizing those, the only vocabulary we have, you will of course need to learn about biconditionals, and then the rest of these are pieces that are frankly polygons, triangles, quadrilaterals, the things that you've seen before, and so it's more of a little bit of a review. And then when you have your practice homework, a lot of the conditionals you're working with are related to triangles, quadrilaterals, and things of that nature, just so that you can refresh your memory on things that you already knew. So your practice will build biconditional statements in the context of stuff you're already familiar with. That way, when we start looking at unfamiliar pieces, you'll already be familiar with the structure. At its most basic level, we have already seen that we could have if P, then Q. That was a conditional statement. We also saw that the converse of that would be if Q, then P. Ultimately, what that's telling us in terms of its symbolic format, the conditional was P implies Q, and if we go backwards, Q implies P, we get the converse. A biconditional, since bi means two, just combines these two things. So instead of having only a forward direction for a conditional, or only a backward direction for the converse, a biconditional is both ways. And so you'll note the notation that we already have. When we use a double-sided arrow, this is a symbol we use for the biconditional. And we can recognize it because we have a forward arrow for the conditional. We have a backward arrow for the converse. And so we're just putting the two together and say, well, if we've got arrows going both ways, it's forward and backward. A second format we will use, especially when we have things written in sentence format, if and only if is how we write this out in English. Anytime a sentence says if and only if, that's the indicator that we are using a biconditional. And because mathematicians like to be lazy and have shortened versions of notation, a double F for if, this means the same thing. IFF is the abbreviation we use for if and only if. Okay, now the first type of thing we want to do is just write out a conditional and write out the biconditional. So, based on this biconditional, an angle is obtuse if and only if its measure is greater than 90 degrees and less than 180. What would the conditional be? Remember, the conditional is the forward direction, so we still need to identify hypothesis and conclusion. If hypothesis, an angle is obtuse, then we need the conclusion. And symbolically, I'm just going to write this out this way. If its measure is between 90 and 180, I'm just trying to cut down on the amount of writing that I have. So 90 is less than the angle is less than 180. And now we want to write out the converse. And so, taking what you're telling me, if the measure of the angle is greater than 90 and less than 180 degrees, then the angle is obtuse. Absolutely valid. We're switching around the hypothesis and conclusion. Completely valid way. By far the most common way that people will write it. I would like to remind you, though, it's not always about what's written first and what's written second. It's about hypothesis and conclusion. Another way that we could have had the conditional written as a converse, get rid of that. And just move the location of the if. By changing the location of the word if from the front to the back, we change the back into the hypothesis. Completely valid way of doing that also. Okay. Now let's try to identify the conditionals. For this one, we have the conditional written already. If 5x minus 8 equals 37, then x equals 9. We want to write out the converse for that statement, and we also want to write the biconditional for that statement. So how would we write out the converse? Well, we could switch around the hypothesis and conclusion, switch out the 1 underline and 2 underline, or we could switch out the if and then. I'm choosing to keep it in the same format, 5x minus 8 equals 37. And we haven't used this format in a little while, so I just want to remind you, we can use the word implies for a conditional. And this is not the converse. The piece that I've written down in the blue is the actual statement itself. You'll notice all I did is switch out if and then with the word implies. To get the converse, we actually need to switch something around. The structure I would take here, x equals 9, implies 5x minus 8 equals 37. And there, that's finished. For a biconditional, we could actually use either one. We could use the conditional, which I had written in blue. We could use the converse, which I have written in red. And for the biconditional, all we have to switch it out with is if and only if. 5x minus 8 equals 37, if and only if x equals 9. And at this point, I want you to pause the video. I'll pause the video, and I'd like you to complete the problem B on your notes. I'll come around and check that. In an effort to save you a little bit of time with some of the writing, I'll write it out here. If two angles have equal measure, then the angles are congruent. Writing the same sentence up symbolically instead of with the written English. Okay, so here in the blue, we had the original statement. for the converse, we need to switch around the hypothesis and the conclusion. And so the red is our converse. For the biconditional, we could use either the red or the blue, but we're just going to put in if and only if. Since a biconditional goes both directions, it doesn't matter which one we have written at the front. It doesn't matter which one we have written at the back. Here's our biconditional, and we're done. This particular one should look pretty familiar because this piece in the green we've already had this year. That is the definition of congruent angles. And in fact, when we write up definitions, and I'll emphasize this again later on in the video, definitions are always biconditionals. Every definition has to go forward, it has to go backward. If it only went one direction, it wouldn't be a definition, it would have to be a theorem or a postulate. Now, we want to be able to evaluate whether a biconditional is true or false. And one of the things that you have to keep in mind, true implies false was the only way for a regular conditional to be overall false. True implies true is overall true. False implies true is overall true. False implies false is overall true. Those were our rules for working with a conditional. We also mentioned that with a conditional, having a false hypothesis didn't really, well, we don't really care about them because with a false hypothesis, they're not useful in any way, so we never work with them. Well, consider what happens when we put in the biconditional with it as well. When we take false implies true, the converse was overall true. For the biconditional itself, the whole thing to be true, both the conditional and the converse have to be true. In this instance, where we have a true biconditional with false, are they both true, forward and backward? No. So this is a situation that will be overall false with a biconditional. Consider what happens with the true implies true case. When we change the direction, true implies true. That's true. And because both directions, forward and backward, are true, that means the overall biconditional, that's overall true as well. When we have the false implies true, we run into the same problem that we had up here. One direction is true, the other direction is false, and so it's overall false as a biconditional. With false implies false, that will be overall true. Realistically though, we're still in that boat where we are working with false statements. We really don't care about those too much. Our focus is going to be a lot more trying to use biconditionals that are the true both direction case. True implies true and the converse. With that in mind, is this overall true or overall false? Remembering that for a biconditional, these are the only ways for a biconditional to be overall true. The front and the back, the hypothesis and conclusion have to match. So, a rectangle has side lengths 12 and 25 if and only if its area is 300. Is that overall true or overall false? Well, with an area with lengths 12 and 25, if we assume that's true, then we get the area. Well, what's 12 times 25? So this is a situation where, and I want to try to clean this up so it's easier for us to see. We recognize the hypothesis, we recognize the conclusion, and so going this direction, this is a false statement. We don't even need to go anywhere else. The forward conditional is false. With a forward conditional being false, it doesn't matter if the other one is. This is already instantly telling us that the overall biconditional is false also. Okay, consider this. A natural number n is odd. Natural numbers are, of course, the ones that you count with. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you keep going. So if we take an odd number, like 3, and then we square it, does that give you an odd result? Nope. 3 times 3 is 9. Okay, based on this example, one example is true. If we took something like 9, 9 times 9 is 81. Does multiplying two odds give you an odd? No. Yes, 81 is odd. If we took 25 times 25, that will equal 625. So it's true here. Right now I'm using inductive reasoning. I'm spotting a pattern by picking several examples. With the 3 examples that I picked, they all wind up being true. So based on inductive reasoning, following that pattern, we can make the guess that this is overall true. Now, I'd like to reemphasize, definitions, whenever we encounter them throughout the rest of the year, definitions are always biconditionals. And so, one example of a definition, a polygon is a closed plane figure formed by 3 or more line segments. This definition is a biconditional. A figure is a polygon if and only if it is a closed plane figure formed by 3 or more line segments. And so what we'd like to take a look at, just to refresh your memory, what are the things that screw you up? Why is it that some of these things on the right are not polygons? For instance, what's wrong with this one? It's the line segments section. A polygon cannot have any curves. It has to be line segments only. What about this part? What's wrong with that? That part's not closed off. A closed polygon does not have any overhanging sections. There are no holes, there are no gaps, they don't cross over each other. And so, not being closed causes a problem here. Not being closed causes a problem with the gap. And what's wrong with the last one? a plane figure is two-dimensional. This is 3D. A three-dimensional figure is not a polygon. And just to refresh your memory, because of course I'm sure you know it, if a polygon has 3 sides, it's a triangle. 4 sides makes it a quadrilateral. Please notice that we have a Venn diagram. I'd like to remind you of one of the things we did when we were working with biconditionals. When we were working with conditionals. We saw a connection writing up a conditional. If something is contained on the inside, for instance, triangles are contained completely inside polygons, we saw visually that this can be represented as a conditional. If it is a triangle, then it is a polygon. And that would be a true statement. On a Venn diagram, we had the inside and outside components, and that would create a true conditional. Please be aware that the same situation will create a false biconditional. If we just switched it around, if it is a polygon, then it is a triangle. That's a false example. It's not true because the quadrilaterals are a bunch of polygons that are not triangles. And so any one of those would serve as our counterexample. Just wanted to refresh your mind, remembering that Venn diagrams do tie into conditionals, and they tie into biconditionals as well. All right, lastly, before we finish off the video, just wanted to have one last reminder. Definitions are always forward and backward. Definitions can be reversible. Whenever we encounter a postulate, though, that's not the same thing as a definition. Many times we will encounter postulates which are only one way. They work going forward, they don't work going backward. And we will encounter those throughout the year.